Looking again at the work done by Max Born on the probabilistic interpretation, we have that the number density was related to this probability density, or some probability per volume. Now, we also saw that that was related to this amplitude squared. We were looking at the example of an electromagnetic wave, and so E in this case was the electric field density, well, electric field strength squared. So we can now relate that to the quantum mechanical wave function psi of x, where we're looking at just the time independent version, and we're saying that that is related to some probability density. Now, we can't just simply look at the total volume because psi is a function of x. So we actually need, if we want to get the total probability over some region, or at least we're only restricted to one dimension, we need to integrate. So this is the Born rule, that to get the probability, you have the integral over the region that you're interested in. And let's say we're looking between x1 to x2. And so you square the wave function and you integrate over that distance. And that's the Born rule. Now, there's also the constraint that the probability of finding something is at most 1, or you have a 100% chance of finding it if you look over all possible regions. So normalization, which basically says that 1 is the largest probability you can get, is when you go over the largest range, which is from x of minus infinity to infinity, you should then get the probability is 1. Okay, and we'll see that with our example, and that example is actually shown in the graph below. This will make much more sense in a minute when we look at the example of the infinite square well and a particle trapped in it. So to be a solution of a Schrödinger equation, there are 3 conditions. We'll write those out. Now, the first one is related to what we just said, which is that as x goes to either positive or negative infinity, then for the particle to be contained somewhere within that range, you need the wave function to actually go to 0. So in other words, if you started to integrate over the wave function, you don't want it to suddenly get very, very large values. It needs to be contained, which is also another way of writing the second condition, which was the normalization. So the normalization that we just showed. And then the third is that because we're dealing with first and second derivatives with respect to x when we're looking at these wave functions, psi of x and the derivative with respect to x must be continuous. So that's just saying that you can take the derivatives. Okay, so those are our 3 conditions. And next we're going to look at an example where we can actually do this analytically and get solutions for the Schrödinger